What is the connection between audio engineering, population dynamics, and artificial intelligence? The answer is that they all use linear algebra. A few videos from now, we will pick an audio signal apart. We're going to use projections, correlations, and other simple linear algebra tricks to pull that off. In order to get there, we first have to figure out what an inner product is, and what the rules for vector spaces are. Then, we will begin to focus on linear transformations, and how they transform vectors in different ways. The main goal here will be to build a simple artificial intelligence algorithm that can discover patterns and new concepts in big amounts of data. These techniques are used for analyzing movie reviews, photos of faces, natural language text, and more. But we will also look at the long-term dynamic behavior of linear systems, such as a pendulum that slowly comes to a halt, or the growth of populations of animals in an ecosystem. So, buckle up, it's going to be an interesting series full of deep connections and real-world applications. So, what exactly does the word linear mean? Geometrically, it means flat or straight. Flat planes and straight lines are linear. A circle is not flat, it's curved. So we don't call it linear. Algebraically, it means that we raise things only to the first power. The equation for a straight line contains x and y, but not x squared or y cubed. The equation of a circle isn't linear because it contains second powers. Without those second powers, the circle would never be able to bend backwards. Straight lines always keep going in the same direction. They never come back. Second-degree polynomials can bend back on themselves, such as this parabola. That's how higher-degree polynomials manage to have multiple zeros. So, the short version is that linear things are straight and flat, and their equations have only first-degree terms. What's the big deal? Why do we care? Well, first of all, linear systems are easy to analyze. When you go shopping, you pay linearly depending on how much you buy. The price of 2 bananas plus 3 apples is 2 times the price of a banana plus 3 times the price of an apple. It's simple. You'll never pay square dollars or euros cubed. You may remember from high school that a linear equation is easy to solve. Just bring the factor to the other side and you're done. Nonlinear equations are a lot harder. The quadratic equation requires a complicated formula to solve, and higher degree equations can often not even be solved, at least not with algebraic formulas. Another big advantage, especially when building bridges and machinery, is that linear systems behave in a simple, predictable way. When a system acts like a straight line, you can easily predict where it will be at any point in the future. You just extrapolate at the same slope as far out as you want. For nonlinear systems, this is not so simple. When you start looping or iterating nonlinear systems, by feeding their output back into their input, you can get all kinds of chaotic behavior. Fractals, chaos, and unpredictability only occur when at least part of a system is nonlinear. So it makes sense that we prefer a world of linear behavior, because that allows us to build more robust stuff, predicting exactly how far it can bend before it breaks. Great! Linear systems are straight, flat, easy to work with, and predictable. The bad news is that many real-life systems are definitely not linear. The Earth isn't flat. Objects fall by tracing parabolas through the air. And when you buy more than 10 apples, you may get a discount, which breaks the linearity and makes it harder to calculate the price of your fruit salad. This is where calculus comes in. You see, when you zoom into the Earth far enough, it starts to look as good as flat. We might even approximate the curved surface of a sphere with a flat plane. When you zoom out again, you can see that the approximation is far from perfect. It makes huge errors when you move away from the point where we started. But as long as we stay close to the tangent point, the tangent plane is a great approximation. Calculus tells us exactly what the best approximation is. We'll talk about that later. We can first focus on stuff that is already linear, knowing that we can safely pretend that many things are at least almost linear. Over the course of the next videos, we're going to look at the math of vectors, matrices, and other linear stuff. I want to make this more concrete and tangible by also showing you many real-life applications. The obvious one is that you can calculate forces on objects by adding together all the vectors that are pulling the object in multiple directions. The sum of all these vectors tells you in which direction the object will be accelerated. Artificial intelligence is making headlines today, and it uses linear algebra much more than you might think. We may talk briefly about neural networks, but I'm much more excited about applications in big data analysis, where the data is stored in lists of numbers. Those lists can be added and scaled just like vectors. The inner product of two such lists will tell us something about how similar they are, so that we can start looking for patterns that allow machines to learn about the world. Once you manage to encode different words of the English language as vectors, you can even calculate with them, to figure out all kinds of linear relationships between concepts of our day-to-day language. This is unexpected and cool. Now, don't get carried away. This simple technique can only detect linear relations between words. As we've seen, many things in real life are not linear, so these word vectors only get us so far. In fact, engineers have deliberately added non-linear components to neural networks to make sure that they can capture the more subtle, bendy, flexible concepts of our everyday language. Here's another important application, one that we will encounter again later in audio engineering and even in quantum physics. When your smartphone plays an audio track, it shows the low and high frequencies in the sound. It decomposes the sound wave into a sum of simple sine waves, each with its own unique frequency. Like ordinary vectors, functions such as sine waves can also be added and scaled. So we can start from a set of sine waves and then add them up to obtain a more interesting, rich, layered sound. We can then use the tools of linear algebra to create audio filters, such as a low-pass filter that only allows the low bass frequencies to pass through. As I close the filter, you will hear the high-pitched sounds dropping away, until only the low-frequency bass sounds remain. In due time, I will explain this all in more detail. First, we need to look at some more abstract algebra stuff. Linear algebra is basically the study of vectors and vector spaces. Many courses and YouTube series focus on the geometry of vectors. I agree that the geometric picture is really important, and it gives a lot of intuition. We will look at geometry in the next chapter. But when dealing with data, such as in artificial intelligence, there isn't always an easy geometric interpretation. We are often dealing with abstract data, or with spaces that have thousands of dimensions that we can't possibly hope to show geometrically. So, out of pure necessity, you should become familiar with the algebra of vectors and matrices too. Algebraically, we always start from a field of numbers. We typically use the reals, but in physics you often see the complex numbers as well. We will focus on real numbers because they make everything easier to visualize later. Vectors are, by definition, objects that we can add and scale. The two operations have to satisfy a number of important properties, but don't get lost too much in the details. This is merely the abstract definition of a vector space, and it makes much more sense to look at concrete examples, so that's what we will do in a moment. For the rest of the series, the main thing to remember is that you can do only two things with vectors. You can add them and you can scale them, nothing else. Surprisingly, this limited set of operations leads to a rich theory, as we will see soon. One thing we cannot do is multiply vectors with each other. In fact, we don't want to do that, because that would introduce higher powers of vectors, which would make them behave in nonlinear ways. So, in case you've ever wondered, this is the reason why we only have addition of vectors, not multiplication. Remember that scaling is perfectly allowed, because it's only a multiplication of a vector with a scalar, not a multiplication between two vectors. We don't explicitly say anything about lengths, angles, and other measurements. The basic rules for vector spaces simply do not allow us to measure anything. That seems like a pretty big restriction, especially for applications like mechanics, audio engineering, and quantum physics. We will have to fix this restriction in the next video by extending the rules for vector spaces with some additional features. Today, in this video, we won't do any of that. For now, the only things you can do with vectors is scale them and add them. But even that limited capability already leads to some impressive results. Quantum physics is arguably one of the most complicated theories that human beings have ever discovered. And yet, it turns out to be surprisingly linear. The main equation of quantum physics, the famous Schrödinger equation, is a linear differential equation. This means that the solutions to this equation behave like vectors. They can be scaled and added. Let's say that you run an experiment with two possible scenarios. Either an electron goes through the left slit, or it goes through the right one. Both of these scenarios are valid solutions to the equations for this experiment. Solutions like this are called wave functions, and they satisfy all the requirements for vectors. In particular, we can add two solutions together, and the rules of quantum physics tell us that the resulting sum will also always be a solution, a possible scenario. So you see that even very simple operations, such as vector addition, can have profound physical impact. In the context of quantum physics, vector addition is called superposition. The electron can be in a superposition of going through the left and the right slit, both. Does this mean that it's in two places at once? Well, I don't really know, actually. Ask me again later. The only point I wanted to make here is that the addition and scaling of vectors are very common, even in the world of tiny elementary particles. And it's all because the Schrödinger equation is linear. Also, this is a great example of abstract vectors. Wave functions are not just the geometric arrows that you see in a typical introduction to linear algebra. They are a completely different species of vectors. We will work with many kinds of vectors in future videos, so it pays off to start with the abstract algebraic definition. But now we can make things a lot more tangible. Geometrically, the easiest way to picture a vector is as an arrow. I'm going to review some of the properties here, but I'll try to make it quick. I assume that you probably already know most of this. If you need a more thorough introduction to vectors, please see the links in the description. To add two arrows together, you just put one of them after the other, and you follow both in sequence. The result goes from the tail of one to the tip of the other. Vector addition is commutative, so adding them in the other order gives us the same result. This is known as the parallelogram rule. When you scale a vector, you just stretch or shrink it along its direction. The number that you multiply the vector with is called a scalar for exactly this reason. Each vector also has an inverse for addition. You obtain it by multiplying the vector with -1, which has the effect of flipping the arrow to the other side. Adding the vector to its own inverse gives us the 0 vector, which you can think of as a weird kind of arrow with no length and pointing in no particular direction. I know I keep using words like length and direction here, even though I warned you that we cannot define those yet. Geometric vectors have a very natural and easy definition for lengths and angles, but other types of vectors don't. So we will introduce a more generic measurement device later. Using that device, we will be able to define lengths and angles for all vectors, not just for arrows. Anyway, now that we have inverses, we can also define subtraction. The result of b minus a is defined as b plus the inverse of a. That's how subtraction is always defined, and it's no different for vectors. So you first have to invert a before adding. It can be cumbersome to have to invert the second vector, so here's an easier trick. The difference between vectors b and a is an arrow that runs from the tip of the second vector, a, to the tip of the first vector, b. You can see that the result is exactly the same. This innocent little trick will become very useful later when we run an object along a trajectory. We want to know how fast the object is moving, and this involves calculating the distance the object has traveled. This is given by the difference between two successive position vectors. Our little trick tells us that this difference will be a vector that runs from the tip of the first position vector to the tip of the second one. As you shrink the time interval between the two positions, their difference becomes a tangent vector. So the velocity of the object is going to be tangent to its trajectory. I won't go into the details here. Just note that the velocity vector is the difference between the positions divided by the time. Time is just a scalar, so it changes the length of the vector, but not its direction. It's cool to see that this advanced vector calculus stuff uses simple operations on vectors that we can already understand. In high school algebra, you have a number of operations at your disposal. You can combine addition, multiplication, and powers to create expressions that look like this. They're called polynomials, and they use the available operations perfectly. We have a sum of products of powers. That's exactly the correct order of operations, so that you can write a polynomial expression without any parentheses. In linear algebra, all we have is addition and scaling. You can combine these two operations into expressions that look like this. This is known as a linear combination. Think of linear combinations as the polynomials of linear algebra. Given our two operations on vectors, this is the most generic expression that you can create. When you start from a single vector, its multiples all lie on a line. This line is often called the span of the vector. So every vector that we can obtain as some number times our vector is said to be in the span of that vector. When you start from two vectors that are not on the same line, you can make linear combinations of those. The resulting vectors all lie on a plane. So this time, the span of the two vectors is a two-dimensional plane. We can easily extend this. When you take three vectors that are linearly independent of each other, their span will be a three-dimensional space, and so on for higher dimensions. Did you notice that the span of a set of geometric vectors is always a straight or flat space? A line is straight. A plane is flat. A three-dimensional space is also flat, although that's harder to see for creatures like ourselves who live inside that space. I already mentioned that geometry on flat spaces is a lot easier than on curved spaces like spheres. So we will often be on the lookout for flat spaces that are spanned by exactly the right number of independent vectors. The number of independent vectors we can find in a space is called the dimension of that space. Lines are one-dimensional because they are spanned by only a single vector. Planes are two-dimensional because you need exactly two independent vectors to span the entire plane. Any third vector inside the plane can be decomposed into the two other ones, so it doesn't give us any additional space to span. Dimension is an incredibly important concept, precisely because it tells us how many independent degrees of freedom we have. When solving equations, we want to know how many unknowns we have, and also how many constraints. This can often tell us, in advance, if the equations can be expected to have a solution, and how many solutions it has. Even Sudoku solvers, like the guys over on Cracking the Cryptic, often count how many degrees of freedom they have left, in order to know if they have an exact solution or not. Each independent constraint that you place on a set of vectors reduces the amount of freedom you have for choosing those vectors. When you start from a two-dimensional plane, you have 2 degrees of freedom, by definition. If you then constrain your vector to lie on a circle, this one constraint removes 1 degree of freedom. You now have only a single degree of freedom left. The angle on the circle can still be freely chosen. Once you pick a specific angle, you have no more freedom left, and you know exactly which vector we're talking about. This balancing act between constraints and degrees of freedom is crucial for many domains of higher math. For example, when you study a swinging pendulum, you could express its position with its x and y coordinates. But the pendulum is constrained. Because it is attached to a wire, it has to move on a circle. This tells us that we have only 1 degree of freedom, so we need only 1 coordinate. We can describe the entire system using only its angle, theta. And just like that, we have pulled a whole new bunch of concepts out of the simple rules for vector spaces. It's remarkable that we only need a field of scalars, 2 operations, and a few simple properties. From this abstract algebraic definition of a vector space, we automatically get important ideas like linear combinations, linear independence, and even something as esoteric as dimensions. One more concept that also emerges out of these rules is the notion of a basis. We're going to use a 2-dimensional plane as our working example, because it's easiest to visualize on a 2-dimensional screen. Everything also works by analogy in higher dimensions. Remember from the rules we saw earlier that each vector space must have a neutral element. It's the 0 vector, which doesn't do anything when you add it to another vector. The first thing we therefore have to do is to pick a special point on the plane to represent this 0 vector. This point is also called the origin of the plane. In physics, vectors are free to move around. When you have an object, such as a pendulum, that is pulled down by gravity, and it's also being pulled by the wire that it's attached to, you typically draw the force vectors at the center of the object. When the object moves somewhere else, you can just move the force vectors along with it. A vector stays the same when you translate it. In linear algebra, however, vectors are, at least in principle, not free to move around. Algebraically, a vector always has to start at the origin. Now, I have to admit that I'm going to be very sloppy with this convention. In practice, mathematicians will very often draw their vectors anywhere they like, and I will do the same. Just remember that when you see a vector hanging somewhere in the plane, in the back of your mind you should always think of it as this translated vector instead, with its tail at the origin. This will become especially important when we transform vectors in an upcoming video. It's also important when talking about the span of a set of vectors, before finding the span of one or more vectors, make sure that you always move them to the origin first. The linear combinations of the vectors always include the zero vector, which proves that any span must always run through the origin. I hope you see a connection with an earlier video here. I want to remind you that a line or plane through the origin is a subgroup of the vector space. Vectors form a group under addition, and its subgroups are always flat spaces through the origin. The cosets are other flat objects parallel to the subgroup, but they never contain the origin, so they can't be subgroups. We can now say something very similar, but this time we think about spaces instead of groups. A vector space, such as the plane, is any set of vectors that can be added and scaled. Well then, let's add and scale some vectors on our line. It should be easy to see that the result is also always on the same line. So the subgroup is closed under addition and scaling. This means that the line is not only a subgroup, but also a subspace. It's closed under the very operations that define vector spaces. In general, the span of any set of vectors will always be a subspace, algebraically speaking, as well as being flat, geometrically speaking. Lines that don't go through the origin don't contain the neutral element, so on top of not being a subgroup, they can't be subspaces either. Okay, that's enough about the origin and subspaces. The next thing we do is to pick as many linearly independent vectors as we can. Since the screen is two-dimensional, we can pick exactly two vectors that are independent of each other. We call these the basis vectors. The multiples of one basis vector create a straight line through the origin. The same happens for the other basis vector. This gives us two axes that intersect at the origin. In this series of videos, we will almost exclusively work with an orthonormal basis, where the basis vectors are orthogonal and of unit length. The advantage of picking a basis is that we can now decompose any vector into a linear combination of the two basis vectors. The coefficients of this linear combination are called the coordinates of the vector in this particular basis. Coordinates are yet another concept that follows from the abstract rules. We usually write the coordinates of a vector in a column with square brackets around it. That's just a convention, but it will influence a lot of the notation further down the line. The decomposition is unique. In a given basis, every vector has one and only one pair of numbers that does the trick. How do you find those numbers? Geometrically, it's very easy to see that you have to project the tip of your vector onto each of the axes, parallel with the other axes. This works even if you pick your basis vectors to be at an angle other than 90 degrees. In the next video, we will discover a very elegant way of computing the coordinates of a vector using the dot product. In the next video after that, we will even project sound waves onto basis sine waves to obtain the frequency spectrum of a sound. So this is nice. Once we pick a basis, we can write all vectors as tuples of scalars. Mathematically speaking, this makes our vector space isomorphic to a set of tuples. We just use the expected addition and scaling operations directly on the numbers, and we can forget about arrows altogether. This makes it easier to perform calculations or to solve equations. However, there is also a major downside to picking a basis, and that is that all your coordinates will only be valid in that basis. The problem is, we could have picked any different basis. Really, any set of two independent vectors will do. And as soon as we pick a different basis, all our coordinates are going to change. Just look at what happens to the coordinates of the same point in different bases. In fact, if you look a bit more closely, you will see something remarkable and extremely important. When I make the basis vectors twice as long, the coordinates will do exactly the opposite. They will become only half as large. It seems as if our coordinates try to undo or compensate for the change in basis. The same thing happens when we rotate our basis 90 degrees counterclockwise. The coordinates of the vector change in the opposite direction, as if they were going clockwise. That's because from the perspective of our rotating basis, the vector indeed seems to go the other way. Imagine yourself standing on the origin and turning together with the axes. You should see the tip of the vector move clockwise. This key behavior of coordinates is called contravariance. The word literally means that the coordinates change in the opposite sense as the basis vectors. This is going to become incredibly useful and important in tensor algebra, where we will spend a lot of time figuring out how to make our calculations invariant, so that they no longer depend on any specific choice of basis. Until then, we have to remember not to get too attached to the exact numbers, because they are completely basis dependent. So yes, we could forget about geometric vectors and just limit ourselves to the study of tuples. But then we lose the basis independence. And so in practice, we will be jumping back and forth between the world of tuples, where calculations are often easier, and the world of geometry, where reasoning about the invariant properties of our vectors will be more natural. One thing that we still cannot do, regardless of which basis we pick, is to measure things. Sure, you can measure relative to your choice of basis. So you can say that this vector is 3 of the first basis vector plus 2 of the second one. But you still cannot say exactly how long it is. You may think that Pythagoras could help you, but remember that your basis vectors may be non-orthogonal. And even in an orthogonal basis, we haven't actually specified yet whether these basis vectors are 5 centimeters or 5 light years long. The rules of vector spaces simply do not allow us to measure anything. So we will have to introduce new features in the next video. Like I mentioned earlier, this has been just a very quick overview of a huge domain of higher math. If you have specific questions, don't hesitate to ask them in the comments. I will do my best to answer them. I can also highly recommend a number of YouTube channels that dive deep into the guts of linear algebra. First, there is the series called Essence of Linear Algebra by 3Blue1Brown. This is a brilliant series with lots of good visuals, and it has come to serve as the de facto introduction to linear algebra on YouTube. It's quite short, which is great if all you need is a quick intuition, but it may also still leave you with lots of open questions. If that's the case, oh boy, do I have a treat for you. Pavel Grinfeld is one of the most brilliant lecturers you can find on the web. His channel is called Math the Beautiful, and I would say that it's criminally underrated. The guy has a passion for math that drips from every sentence, and he has the uncanny talent to make anything seem easy and logical. So, for those of you who need linear algebra in your studies, or who want to finally understand every last detail, this is definitely the place to go. His videos may get a bit slow now and then, but I promise you it's worth your time. I carefully collected many other useful links in the description as well. And as usual, please subscribe, like, share, bake me a cheesecake, comment below, and support the channel in any other way that you can. Next time we'll talk about the dot product. This is going to lead up to a very cool video about Fourier analysis and sound filtering. You can already watch all of that on Patreon if you're curious. After that, we're also going to apply vectors to artificial intelligence, and we're going to start getting our first glimpses of the symmetries of the universe. Stay tuned, And whatever you do, always keep learning.